What's up, Warriors? Hope you are doing well. Today we are going to rock with some operations management. Just want to do a manual simulation of what happens when we have bottleneck. Okay? So I figured this was the best way to do it. First, let's get oriented on what we're talking about. So we're talking about a product layout, and we're going to just use our example that we talked about in class where we're making batarangs. Remember that good old batarang looks something like this. Batman throws it at the bad guys. So we have cut, we have shape. We first cut the steel and then we shape it into that batarang, and then we subdue it. We make that nice matte black. Looks pretty cool. And we said that things are fine when all of these steps take 2 minutes. That takes 2 minutes. This takes 2 minutes. This takes 2 minutes. Meaning that this station works on a batarang for 2 minutes and then they pass it to the shape station. And at the same time, they begin a new one. And then the shape station works on it for 2 minutes and then they pass it. And everything keeps moving every 2 minutes. And in that case, we don't have a bottleneck. But let's suppose, like we did in class, that this isn't 2, and this is something like 5. And if that's the case, we have a bottleneck, and we start getting buildup right here. And the other thing we talked about in class, that as long as we keep pushing batarangs into the system, meaning that we begin a new batarang every time this is open, we'll continue to have that buildup. But regardless, the output, the system's capacity, will be regulated by the bottleneck, and that will be 1 batarang every 5 minutes, meaning that the system pumps out a finished batarang every 5 minutes. It doesn't mean that 1 batarang takes 5 minutes to go through the process. It means that if we stand here and count the amount of time that passes between 1 batarang exiting and the next one, it'll be a 5-minute interval. It also means that we can define this regulates capacity, and so we can therefore define the capacity of the system in accordance with this right here, which is what I call the cornerstone, and any kind of time period that we're talking about. If we want to know how many batarangs per hour, we would use this. If we want to know how many batarangs per day, we just need to know how many hours we work in the day. We're probably not going to work 24 hours a day, although Batman might, and so on and so forth. So the purpose of this video is to show how this buildup occurs and to reinforce that, yes, as long as we have this 2-5-2 structure, 1 batarang will exit the system at a 5-minute spread. Okay? So that's what I'm going to do now. So here we are in Excel, and again, the purpose of this is to show you how there's that 5-minute interval between batarangs being produced by this system. So I've just inserted the screenshot of our system here so we can refer to that. And I'm going to put these steps in our process up here. I'm going to put cut. And I'm going to put shape. And subdue. And then I'm going to have a column for when the batarangs exit the process. Get a little more length there so we have a little more room. And you notice I left a column between these two because we know there's going to be buildup right there. So I'm just going to put a weight right there because I want to show you where those batarangs go when they're waiting to be shaped. Okay. The other thing I'm going to do here is put this is a minute begin, and this is a minute end. And so what that means is that this is simply when the minute begins and ends. So for example, we start at time 0, and then this is the end of the first minute. Okay, so 1 minute has elapsed. And then this would be the start of that first minute. Okay, so it's really the start of the second minute because these two represent the first minute is complete. And so this is the second minute elapsing. And that's the end of the second minute. So as long as you grasp that these are minutes passing in time, we'll be good to go. Okay, so I think we have everything ready to go right here, and we're just going to label batarangs by letter. That's a little bit less confusing, and then I'll color code them as well. So we begin first production of the day. There's no work left over from last night or any batarangs already in the system. All the tables are clear, and we are ready to go produce some badass batarangs. So here we go. So the A batarang, which is our first batarang of the day, enters the system at time 0. And it's going to spend 2 minutes there in the cut station. So at the end of the first minute, it's there, and at the end of the second minute, it spends the second minute there. At the end of the second minute, it doesn't have to wait because there's nothing in front of it. It moves to the shape station, and it's going to spend 5 minutes there. And at the end of the 5 minutes it spends in the shape station, it's going to move to the subdue station and spend 2 minutes there. And then at the end of that minute, the beginning of the next minute, it's going to exit the system. And so the first batarang of the day, exit the system at 9 minutes. Okay, and we can see here we're at the beginning of the 9th minute. If we started a stopwatch, our stopwatch would say 9:00 is when that first one comes out. Okay, and I'm just going to get some reference markers here just so you can follow along, and this is nice and clear. And I'm just going to color code A yellow, so you can see how things progress. Now, before we move on, remember the definition of throughput is 1 batarang through the system, assuming no waiting. And so we have that here because A, there's nothing in front of it. It didn't have to wait. And so that 2 plus 5 plus 2 is indeed 9. And that's how long it takes. It starts at time 0 and it exits at 9 minutes. Super. The problem comes when we enter the next batarang into the system. Okay, so we need to think about this. As soon as the cut station becomes open is the beginning of the second minute, or actually the beginning of the third minute. Okay, and we put B into the system. And B is going to spend 2 minutes in that cut station. Well, the problem is that when B is done at the cut station, it can't go over here to the shape station because the shape station is occupied. So B has to sit here in the waiting room, kind of like at the hospital when you're trying to see the doctor, but the doctor's seeing another patient. So B has to wait there until A becomes open. And A doesn't become open, or excuse me, the shape station becomes open. And the shape station does not become open until down here at the beginning of the 7th minute. Okay? Now, the B batarang is going to spend 5 minutes in the shape station because that's how long is required. So 1, 2, 3, 4, 5. Okay? And then it's going to move on to the subdue station and spend 2 minutes there. 1, 2. And then it's going to exit the system. So while you're consuming that or digesting that, I'm just going to go ahead and color code for clarity how B is moving or flowing through the system or not flowing. So let's highlight a couple things left to right. Number 1, B is frustrated here for 3 minutes, meaning that it's spending 3 minutes in the waiting area here, whether we had one designated or not. Hopefully we had one designated, kind of get that batarang out of the way, know it's there. If the batarang was a huge batarang, this would start to become a problem because it might be unsafe and things like that. So that's the first thing, is that B spends 3 minutes in the waiting area. You notice that B is spending more time in the system than A was because B had to wait. Another thing I wanted to highlight was that look at whoever's working at the subdue station. So compared to the shape station, this person or people working here, they are occupied. Once they get going after that first batarang, they are going to be working nonstop. And also while they're working on one batarang, they can see that they have another one waiting on them. So that's not, if we can avoid that, that's not a good thing to have. We eventually want to do something about that, because how would you feel if you're working and you know that the second you're done with something, you have to begin work on another thing, and that's how your life is going to look like for the rest of your shift? That's not a very that doesn't motivate you to really do the right thing, and actually motivates you to cut corners and potentially start building defective batarangs, which is what we do not want. The other thing I would like to highlight, that in contrast to the shape station, the subdue station is not occupied. So it finishes a batarang A, kicks it out of the system, and then it has this 3-minute kind of break time. And so some of you have mentioned, well, that's when the subdue should go over and help the shape, and that could happen. Okay, but if that's not something we influence to have happen, the subdue station is kind of getting over a little bit. Okay, and then the last thing I wanted to highlight was this spread here. So as we can see, B exits the system at the beginning of minute 14. And that's that 5-minute spread that I was talking about. I'm just going to put 5 out here, which means that if we stand out here, we see the first batarang of the day exit at 9 minutes, but then the second one exits 5 minutes later. And that 5-minute interval, that is the bottleneck dictating that interval. And therefore, that interval is the capacity, the one batarang every 5 minutes. Let's take a look at C if we continue with this pattern. So C enters the system, and then it too has to wait. Now, it doesn't have to wait just because B is there. B is going to be there, assuming that we have enough space in the waiting room for more than one batarang. And we see that sometimes in places like barbershops and hospitals, that we don't have enough space in the waiting room, or even a drive-through. You see the drive-through at Starbucks sometimes becomes backed out into the road and actually stops traffic. But for this, we're going to assume that the C can wait there. We could put B comma C right here. In fact, I'll just go ahead and do that. B is going to move out of there, so we'll still have C there, and C will be waiting even longer than B had to. Okay, another minute there, in addition to these. And then C is going to be able to move into the shape station. It'll spend 5 minutes there, and then move out. into subdue for 2, and then down here, it will exit the system at the beginning of 19 minutes. And again, we see that separation here of 5 minutes between each one. So we see B come out at the beginning of 14 minutes. We wait, and then we see C come out at the beginning of 19 minutes. So C has to wait even longer. If I could color code this one on the fly, multicolored, we'd see C waits even longer than B does. And we also see that 5-minute separation. And finally, just to reinforce the point, let's do our 4th batarang, assuming that we continue to push batarangs into the system. D would go here. This would be C comma D. This would be C comma D. This would be C comma D, and so forth. But then D would wait even longer until that shape is available, and then exit the system down here at the beginning of the 24th minute. And again, see that 5-minute separation. So look how long D is spending in the station. Waiting. 1, 2, 3, 4, 5, 6, 7, 8, 9, compared to the 5 that C was spending, or 6. So it doesn't get any better, is the bottom line. As we go along with this pattern, the buildup there between cut and shape just gets worse and worse. The people working at shape probably get pretty stressed out. Just human tendency, they try to probably find shortcuts so that they can move things along faster. But shortcuts in a production process aren't always a good thing. And sometimes they lead to defective product. In this case, batarang, which a defective batarang is just not a good thing. I mean, Batman's not going to be happy with it. Bad guys are, but that's exactly the wrong direction of what we want, where we want to go. So, what I've demonstrated here is that 5-minute separation. Now, what I want to do now is show how we could pull batarangs into the system and get rid of this waiting thing going on. Now, when we pull items into the system, so we're making the assumption that we can't reduce this 5. Ultimately, we would want to reduce this 5. Even if we could reduce it down to 4, that would be great. That would improve our capacity. We'd have one batarang coming out every 4 minutes. Ultimately, we would want to decrease the time required to shape batarangs down to 2 minutes. That would not only increase our capacity, but that would get rid of this bottleneck and this buildup here that I've highlighted. But let's assume we can't do that. It's 5, and we can't, with the resources we have, we can't get it any lower than 5. Well, one thing we can do is to get rid of this waiting by pulling items in to the system. So I'll show you how we could do that. I'm going to copy this and put it at the end here. And I'm going to label our first sheet. This is the the push version. And this is the pull. Okay, and pull method is very much of a lean manufacturing method and makes a lot of sense when you see it happen. So we're just going to start fresh. Let's see here. We don't need to fully start fresh. We will still keep our first batarang of the day. That's not going to change. But I'm just going to freshen up everything else. We can leave that there. We'll take these out for now. And we'll get rid of that there. Okay. So we still have our first batarang of the day. I'm just going to leave the weight up here, but the idea is to reduce any kind of waiting time. Okay, so we got to be a little bit creative and think about, okay, we have to backwards plan the flow based on the bottleneck, and that is the key. So again, we're assuming we can't reduce that bottleneck of 5 within the shape station. So we would want B to move right in here. So I'm just going to put B first. That's our second batarang of the day. Okay, and then B would go here and exit at the same place that it did before. So again, it's not going to increase our capacity. Pulling items into the system is not going to increase our capacity, unfortunately. But pulling the items into the system will reduce waiting, which potentially will preserve quality batarangs because the shape station isn't so stressed out with this big buildup that's happening. So if we want the B to flow into the station here, we need it to be done with the cut station here. Okay, so let's make some notes. A begins at time 0. And B begins at time 5. So, and let's just mark our different colors. I can't remember what B was before, but doesn't matter. Just so you can see that B is different. Okay, so A begins at time 0. I'm just gonna, let's go a little yellow here. And B begins at time 5. Okay, and so C ought to probably begin, I'm guessing time, let's see, that'd be 1 minute, 2, 3, 4. Probably there would be a 5-minute separation or 10. Let's check it out. So same, if we want C to flow in here, flow on out, it flows out at the beginning of the 19th minute, which is that 5-minute separation. We know C should flow in there. So C should flow in at the beginning of the 10th minute. And again, what's the point of all this? Does it increase the capacity? No. As long as that 5 is 5, we're not going to be able to increase the capacity. But what we can do is influence and actually get rid of the amount of weight. Look, there's nothing in that column. Okay, and that's because we're pulling items into the system in accordance with the tempo of the bottleneck. And that is with the theory, we call this the drum. Where we have bottleneck, it serves as the drum of the system. If that drum beat only happens every 5 minutes, that means that an item is exiting the system every 5 minutes, but it also means that we should begin an item at 5-minute intervals. That's obviously synchronized with the input and output of the system. Okay? If we did D, let's just do D. It'll be the same. Let's just do it a different way this time. Here we have 1, 2, 3, 4, 5. We begin a new one. 1, 2, 3, 4, 5. We begin a new one. 1, 2, 3, 4, 5. And here we should begin a new one. Let's see if it works. No waiting, flows right in. We are good in the hood. Comes out here at the beginning of the 23rd minute. No, I missed one here. My bad. Right there. Boom, boom, and boom. Comes out at the beginning of the 24th minute. All right. So there you have it. Just a demonstration of a couple things. One, when we push items into the system and we have a system with bottleneck, number one, how the bottleneck regulates the capacity of the system. But number two, how we have a lot of buildup here as part of that bottleneck, just like a traffic jam. And if we want to get rid of that buildup, we're still going to have the actual bottlenecking itself, but how we could mitigate the impact of the bottleneck is to pull, instead of this here, or this right here, we want to pull items into the system. And that'll clean that up. It won't increase the capacity. As long as that 5 is 5, we're still going to have that limitation on our entire system and our output. But we can get rid of all that buildup there and maybe just make the shape station's life or the bottleneck station's life a little bit more manageable until we can get the additional resources to knock that 5 down to a 4 or lower. So I hope this video was helpful for you and that you enjoyed it. If you have any comments on it, on how it could be better, or maybe I should teach with this method in the future, which is what I'm thinking about as I'm doing this, please let me know. I always value your feedback. And most importantly, rock on with those mad skills and have a great day. Thank you.